Good morning, Internet. I am Matt Booyak, and this is the second video in my series on big integers in C and C++. So in the last video, we wrote a basic big integer class with support for division by small integers. And that may seem like kind of a strange place to start. You might have guessed that we would start with addition, for example, instead. But we're motivated by the fact that division by small integers, and in particular division by 10, can let us calculate the digits of a large integer. Also, we're working eventually toward a solution to problem 20 from the Project Euler problem archive. And this problem asks us to find the sum of the digits of 100 factorial. And so now we have the ability to find the digits of a large integer. However, in order to solve this problem, we're also going to need support for basic multiplication in order to calculate 100 factorial in the first place. And so that's going to be the focus of this video. So let's get into it. Now, before we jump into writing code, there's a little bit of theory we're going to have to cover. And so I want to make a new directory here called notes. And we had previously made some notes about Pythagorean triples. And so I'm going to just move that file into our notes directory. And then I'm also going to create a new bigint.txt to keep our notes about big integers. Now, when I previously covered the algorithm used for division, that was for problem number 16. So let's also pull up that file. Okay, and you'll recall that we went over an example of long division to remember how we could implement that algorithm. If you haven't seen that video, I'd highly recommend watching that before continuing with this video. It's perhaps even more important in terms of the theory and background than the previous video, and so I'll put a link to that in the description if you're interested. But taking the sort of the same approach that we took with division, we're going to look at a basic example of multiplication to get some inspiration for how we could implement that for our big integer class. So let's just say note C problem number 16 for division. And then here we'll say multiplication. Okay, so we used the example for problem number 16 of 12,345 divided by 7. So for this problem, we're going to do something similar, 12,345 times 7. So we'll just go over here. Like so. All right, so in the previous videos, when I was talking about division, I presented this sort of mantra of divide, multiply, subtract, bring down, which is the process that we use to do this repeated division. Excuse me, this long division. And I specifically remember having this drilled into me when I was in elementary school. I don't know if it's the same method being used today. I don't know if it was a common method 20 years ago, but in any case, this is the sort of mantra I learned for doing long division. And I don't recall learning a similar mantra for multiplication, so I'm just going to make one up. It's going to be something like multiply, add, carry, something like that. And I'll explain what that means in just one moment. So let's start going through the process here. We're going to multiply each digit of our big integer by our small integer. You'll note that our small integer is just a single digit. For now, that will be a requirement. Eventually, we'll want to be able to, multiply by, 127 or whatever. But for now, we're just doing multiplication by a single digit. Okay, so let's start 7 times 5. That's going to give us, down here, we'll have 35. And so the next step is add. And for now, our carry digit is just going to be 0. Up here. And so up at the top here, we'll keep track of our carry digit. Let me just separate those, like so. Okay, so our carry digit is 0, and so we're just going to add 0 to 35. It stays the same, and then we're going to carry this 3 up here. All right, continuing, we have 7 times 4 is 28. And now we can add our carry digit. That gives us 31, and we'll carry this 1 up here. 7 times 3 is 21, and add 3, carry the 2. 7 times 2 is 14. And then add our carry, 16, and carry the 1. Multiply 7 times 1 gives us 7, and add our carry to get 8. Okay, so that's the basic procedure for multiplying a big integer by a single digit. And we can just check real quick to make sure that I haven't made any mistakes here. Let's do 1, 2, 3, 4, 5 times 7. And you can see that our procedure matches the calculator here. Okay, so we're going to want to implement something similar in our big integer class. So let's pull that up. You'll recall we put that in our common directory. And so here we have our divmod function that we implemented last time. So we're just going to add multiply, and that's going to take a uint8t as its argument. So this is going to multiply in place our big integer, rather than, for example, returning the result as a value. In that sense, you'll notice that my operators are of the form, this is like the times equals operator if we're talking about standard integer operations, and this is more like the the divide equals operator. Okay, so let's go over to our source code. And we'll add that just after our divmod function here. Okay, so there's some similarities between our division implementation and what we want to do with multiplication. In particular, we're going to have this accumulator, which is sort of the our current working number. If we go back to our notes, there we go. You'll recall that, for example, after we after we did the first few steps, we had this 35, and then we added 28, and so this was 1, and then we had we had 28, and so this here was sort of our current working number, and that's what we use our accumulator for. Just put that back. And that's the same thing we used it for in our division. If we go back to our analysis here, the accumulator would correspond to this value here or this value here. And so that's sort of similar between the two algorithms. And likewise, our remainder is analogous to our carry. And so yeah, there's some similarities between the two algorithms. So we're going to have our accumulator and our carry. Start that off as 0. And we'll need an index to iterate over the cells. And as before, we'll say for I equals 0, I is actually this is something that's a little bit different from division and multiplication. Division, we're working from the left-hand side. Multiplication, we're working from the right-hand side. And so yeah, let's then cells.size plus I. Okay, so remember our mantra here. If we go back to our notes here, is multiply, add, and then carry. And so first we're going to load our accumulator from our number. So we'll say accumulator equals we'll say read cell I. And then we're going to multiply that by our argument n and add our carry. So that's we've done our multiply and add. Now we need to do our carry step. That is extracting the new carry digit from our accumulator. So we'll say carry is equal to accumulator shift right 4. All right, so where does this come from? You may recall if you watched the previous video that our big integer is working in base 16. That is hexadecimal. Going back to our problem 16 analysis, I described how there are different bases. Decimal is base 10, our familiar number system. You have binary, which is base 2, and hexadecimal, which is base 16. And so our big integer works in base 16. Again, if you haven't seen that video, highly recommend. Okay, so that's why we're shifting right by 4 here. This is the same as saying divided by 16. Anytime you're multiplying or dividing by a power of 2, you can use a shift operator instead. And so we'll say shift right 4. Okay, and then we can write our new value. So we'll say write cell I accumulator and 0xf. So similarly to how we were dividing by 16 by doing this right shift, this is equivalent to doing mod 16. And as I said before, like anytime you're taking the remainder mod a power of 2, there's an equivalent operation using this bitwise AND operator. The reason why we use f, going back to our analysis here, in hexadecimal f corresponds to 15, which in binary is 1111. And so this is basically saying give us the bottom 4 bits, which is equivalent to taking the remainder mod 16. Okay, so we've done our multiplication, our addition, our carry, and we wrote our result. There's just one thing left to do, and that is we may have a carry here at the end, and that also needs to be written back to our number. And so we'll say write cell, cell.size carry. Okay. There is one minor optimization that we can make here. You'll see down here in our write cells, if for example we were to write a 0 to the 10,000th cell, currently that would cause us to expand our big integer to be 10,000 cells in size. But it's a 0, so that's not actually required. And so we can add a minor optimization here to say, if index is greater than or equal to cells.size and val, that is val is non-zero, then we'll do this expansion. This will come into play if we have a carry of 0. For example, at the in our notes here, we had at the end a carry of 0, and so we didn't actually expand the size of our integer in terms of digits. And so likewise here, if carry is 0, this optimization here will prevent us from expanding our big int unnecessarily. Okay, so we have our multiply here. Let's add a little bit of code to exercise that. So if we open up our big int test that we wrote last time, you'll recall that this is essentially just a solution for problem number 16. Going back to the problem list here, problem 16 is very similar to problem number 20. It asks us to find the sum of the digits of 2 to the 1,000th. But we're actually able to construct 2 to the 1,000th without using multiplication. And so we were able to solve this problem even though we didn't have multiplication. Now that we do have multiplication, we can solve this in a little bit of a more natural way. This line here, write cell, write 1 to cell number 250. It's a little unclear why that works, and so instead, what we probably want to do is say, for I is 0, I is less than 1,000, increment I, and then we'll just say n dot multiply 2. And we want to say write cell 0 to be 1. So this is a little bit more intuitive, perhaps. We're initializing our number to 1, and then we're repeatedly multiplying by 2 to get 2 to the 1,000th. So let's just make sure that we haven't broken anything here. Let's go to, excuse me, make our library. Oh, I've made a minor typo here. This should be cells.size. And I've made the same mistake down here. Okay. All right, that gives us the answer 1,366. And just in case you didn't see the last few videos, that is the correct response or answer. Okay, so our multiplication seems to be working well, but there are a few things that we would like to clean up before we wrap up this video. And so the first is that allowing our user or the user of the big int class to write directly to cells is kind of bad design. typically, anytime you're allowing your class user to write directly to your private members, even through an accessor like that, it's asking for trouble. In particular, for example, when we were saying, you know, write cell 251, this was we were basically, you know, writing 2 to the 1,000th. But this is only true if we're working in hexadecimal. If we're working in some other base, this doesn't work. And so requiring the user to know what base you're using internally in your class, again, asking for trouble, because you might decide to change that implementation, and you shouldn't require your users, that is the user of your code, to know all the details of your implementation, because that's one of the reasons we have a class to begin with, is to avoid you know, having to know all the details of the implementation for every algorithm and every piece of code. Okay, so we would like to clean this up a little bit. And the way we're going to do that is to allow our class to be initialized to a small integer, which then we can, you know, operate on to create our big integer. And so we're going to go back to our class here, and we're going to move these to make them private. That is, only other class methods now have access to those. But we're also going to allow our constructor to take an initial value, call it val. But we want our existing code to keep working. You know, if somebody's creating an integer without specifying a value, we want it to still compile. And so we're going to use the idea of a default argument. So this is saying if no value is specified, just assume that it's 0, which is the current behavior anyway. So let's go over to our implementation and add our argument here. And then we'll just say write cell 0 val. Okay. And then we don't need this anymore. We do, however, need to pass the value 1 to our constructor to initialize our big integer. Okay, we still get the same answer. Great. Okay, so there's one other thing that that we're going to need to clean up before we can finish this video, and that is right now our use of hexadecimal is a little bit not robust. And the reason for that is that all of our arguments are 8-bit integers, but we actually only support 4-bit integers. And so this is going to break for for values larger than or equal to 16 potentially. In particular, if we're trying to form the number 100 factorial, obviously we're going to need to multiply by numbers larger than 16. And so we're going to want to change the base that we use for our class from hexadecimal to something larger. Really, the only reason I used hexadecimal to start is that it's easier to understand and it was more convenient for the problem that we were solving at the time. Now, I do want to take a brief aside because I discovered something quite interesting when I was trying to come up with a way to show how this breaks. And let me just show you that briefly. So let's go here, and we'll call this yeah, let's just make a little side thing here. We'll call it side test. Actually, let's just abduct our existing code here. Okay, so let's set this to like 15. We'll just make a note so we can put things back. Was 1. And then we're going to say n dot multiply 100. Again, this is just, I want to show you how we can break our class and how it's not robust under certain circumstances. And so, we're going to be calculating this, but let's just print out the digit here. So you would think that this would break because we're multiplying by a number that is larger than our supported base. So you would think that this would break things, but actually it works out just fine. It's in reverse order as expected, but it gives us 1500, which is 15 times 100. That's correct. And so it's a little bit of a head scratcher why that's not breaking. Now here's the fun part. If I say multiply 100 again, so this should give us 150,000, but it gives us garbage. Huh, that's interesting. And it turns out that what's happening is that it's we're actually still storing everything correctly, except the largest digit is being allowed to exceed 16. And so that's okay until it exceeds 255, which is the largest 8-bit value. And so I'm not going to dig into all the technical details as to why it fails in that way, but there is one particularly interesting point that I wanted to call attention to, and that's this line here. This is actually the only reason I'm going off on this big aside is because I actually learned something new in the process of preparing this video, and I just have to share it with you. This is an 8-bit value, and this is an 8-bit value. And so you would expect that when multiplying these two together, it would truncate it to 8 bits. In particular, when it's multiplying 15 by 100, you would expect that would be truncated to 8 bits, or that it would basically take mod 256. And then you have this 32-bit carryover here. It turns out that's not relevant. But it's curious that that's not actually what happens. It actually expands this to a 32-bit integer because it's being assigned to a 32-bit integer. And that's not always the case. That doesn't actually always happen. So there's this whole process of implicit type conversion in in C and C++, where, like, for example, suppose we had, ignore this carry, but suppose this n were a 32-bit integer. Then the compiler would look at this and say, we have an 8-bit value, a 32-bit value. Let's do implicit type conversion to convert this 8-bit value to a 32-bit value. But that's not what's happening here. As best I can tell, it has to do with the fact that that we're on a 32-bit architecture and we're assigning to a 32-bit value. And so it does the promotion anyway, even though both of these are 8-bit values. This doesn't happen if, for example, if these were two 32-bit values and this were a 64-bit value. That doesn't happen. Like, this isn't normal. And I was very surprised to see this. I don't know. I haven't been able to confirm if this is required by the spec, or if this is a quirk of the compiler I'm using, but I just had to share that with you. That this is the only reason why my example of 100 times 15 didn't break things, is because this line didn't actually behave as I expected. But anyway, I'll thank you for indulging my my tangent there. The lesson that I would take away from this is that always do explicit type conversion. If you expect your result to be promoted to a larger value, always it's real easy to just be like, uint 32t and make it explicit, because if you think you know how the rules work, you probably don't, unless you're actually working like on the C and C++ standards committee. You probably don't actually know how it works as well as you think you do. C and C++ have 1,001 corner cases, and the lesson is just don't go there. Like, if you think you're going to go into a corner case, make it explicit what you're doing, because even if you know all the rules backward and forward, the next person who reads your code won't. And so just make it easy for them. Don't rely on corner case behavior. Okay. Let me just make sure that I've gotten this back to the way that it was supposed to be. Yeah, there we go. Okay. So after that side tangent, we're now going to switch our code to using base 2 to the 32nd rather than base 16. And we could just change to using base 256. That would be a perfectly valid way of doing it. That would allow us to solve our problem. That would be that would prevent invalid inputs, like the sort of class breaking behavior that we were just doing. But the architecture that we're on natively works with 32-bit values, and so it makes sense to use that as the as our base instead of base 2 to the 8th. Okay, so let's just go through, and we're going to say uint 8t, and we're just going to replace that with uint 32t. Great. Now, there are a few corner cases that we have to be careful about. In particular, you'll recall that our accumulator needs to be able to hold 2 digits at once. And so let's make that a 64-bit integer. And likewise for our multiplication here. Okay. Also, when we're breaking up our when we're forming our accumulator from our remainder and our bring down value here, we need to now shift by 32 instead of 4. And this gets into an example of what I was just talking about, where this is a 32-bit value. I'm pretty sure that if you shift a 32-bit value by 32, you actually end up with the same value you started with. Another reasonable guess would be that it would be 0. I'm pretty sure it's not. I'm pretty sure it actually works out to be the value you started with. But in either case, that's not what we want. We want it to shift over into a 64-bit value. And so let's just make our remainder 64-bit also. This gets back to what I was talking about, avoiding implicit type conversion in cases like this, where you're expecting it to be promoted to a larger type. Just make it explicit. Okay. So the other change we're going to have to make is down here. There are actually a couple of changes. So this case here, as I mentioned, this does not work for if these are two 32-bit values. This will truncate. This will not give you what you expect. And so we have to do, we have to specifically convert this to a uint64t. We want this to be shift right by 32. And we want this mask to be FFFF, FFFF. Again, this is basically just saying mod 2 to the 32nd. These are all, analogous to what we were doing before, just with a larger base. Okay, so I believe, let me just give this a once-over and make sure I haven't missed any overflow cases here. I think, I think everything should be as expected. Okay, now we'll just need to update our header file. Okay, and if we go back to our test, I don't know that there's anything we have to change about our test. No, I think that should all work just fine. Okay, so let's rebuild our library. Rebuild our tests. Okay, and that gives us the answer that we were looking for. Just as a side note, I do want to, and I should have left my changes up here, but I just want to show you real quick that with this this updated version of the class, that the bad behavior that I was exploiting before doesn't work anymore. So if we do n multiply 100, and we do that twice, and we say printf you can see now it gives us that 150,000 as we expected. And so this fixes the problems we were having with our class before. Okay, so now we have basic division, we have basic multiplication, and so we should be able to move on to problem number 20. And so you can look for that in the next video.